Okay, you can go ahead. Thank you.
Thanks, all.
Thank you for being here. So today we have Monika Lendl from the Observatory of Geneva, also happens to be my PhD advisor. So Monika did her PhD at the Observatory of Geneva, then she moved to Liège in the Austrian Academy of Science for her postdoc, after as a project leader. And then she moved back to Geneva, first as a research scientist, and since 2024 as an associate professor with the Excellencia, which is the Swiss equivalent of the starting ERC grant. And also she's a CHEOPS mission scientist. And since 2023, I think so, yes. And today she will talk to us about CHEOPS and PLATO. So, okay, thank you.
Okay, yeah, thank you very much. It's really a pleasure to be here, to meet all of you, and to be in an air-conditioned environment. We don't currently have air conditioning where I usually work, so this is fantastic. All right, so you all know these guys, right? The planets of our solar system. They're really amazing. We can take such detailed pictures of their atmosphere. We can actually see the little, small-scale structures. We can even go land on their surfaces. We can collect little probes of material and then perhaps never bring it back to Earth, but that's a whole different story. However, now when we go to the exoplanet world, of course, we are very far from this type of detailed study, right? So the best kind of direct imaging of planets is sort of what we get there, right? We have little blobs. Sometimes we can take spectra of these little blobs, but we have no actual surface resolution of these exoplanets. And there's only very few systems that we can image directly, and they're typically young planets, massive planets, and not very much like, Earth or the smaller planets in our solar system. So what I will be talking about are actually indirectly detected planets. And most of you are probably familiar with the two main methods of indirectly detecting exoplanets. I'm repeating them here to make sure that everyone is on board on what I'm going to talk about later. There's the transit method, where we're monitoring the brightness of a star, and then when the planet passes in front, we see this characteristic flux drop as the planet occults part of the stellar disk. And quite clearly, the larger the planet, the deeper that flux loss. So this gives us the planetary radius. And then there is the famous radial velocity method, where we're observing the spectrum of the star and the exact Doppler shift of the lines in that spectrum. And as planet and star orbit around their common center of mass, well, the spectral lines are going to be periodically redshifted. And this, of course, is proportional to the mass of the exoplanet. So transits and radial velocities together are really fantastic because they give us the planetary density. Most of what I'm going to talk about here is going to be transiting planets. So planets that have the orbits nicely aligned so that they pass in front of their host star, as seen from our vantage point. All right, so transiting planets are fantastic. We get mass and radius. And this is really useful because we can start having population studies that study these properties. And so this is from by now, I would say, pretty famous paper from 2020, where we can really see that planets that are predominantly rocky and planets that do have a substantial water or volatile mass fraction, they do follow two different mass radius relations. We can also characterize the atmospheres of transiting planets. We can measure how the stellar light is filtered through the planetary atmosphere during transit, but we can also measure the light coming from the planet when it nears secondary eclipse. And then we can see the flux drop during secondary eclipse when we're suddenly no longer seeing the planet. And then finally, we can study the orbital alignment of transiting planets by observing their transits in radial velocity. And that tells us which part of the blue and redshifted stellar photosphere are occulted by the planet, and therefore tells us something about the direction in which the planet goes across the star and about the orientation between the planetary orbit and the stellar spin. So far, so good. But in order to do all this meaningfully, of course, we really rely on a large population of exoplanets. And so this is the classical video that shows us how our parameter space, period, and mass here is filling up with planet detections as time goes along. As you can see, I should have probably updated this plot. It only goes until 2022. That's on me. But the main characteristics here are there. You can see that we have this population of Jupiter-like planets. They are far out. They're typically detected by radial velocities, and they are quite massive. Then we have this very curious population of giant planets that have somehow made it very, very close to their host stars. We call them the hot Jupiters. And then we have also found that there's this huge population of planets, Neptunes and sub-Neptunes, at relatively short orbital period, right? The Earth would be here. So this is a planetary period of less than a year, and there's a lot of these intermediate size planets sitting in that period range. And then, of course, we are discovering more and more rocky planets as time goes along, including some of them that are really, really close to their host stars and that are practically lava worlds because they're so hot. All right, so actually this population of planets directly points us to a couple of physical questions that we would like to understand. First off, there are these hot Jupiters, and they're really extreme worlds. They're also relatively rare. Only 1% of stars possess a hot Jupiter, but they're very characterizable due to their hot, large atmospheres. And so we can study their climates in a lot of detail, and we can also try and identify the impact of whatever migration has happened here in the composition of the planetary atmospheres to understand how exactly these processes function. Then there are these long period planets. And I will come to that a lot when talking about Plato, but I really want you to understand that we still have this detection bias here, right? Massive planets, we've detected a lot of them with radial velocities, but of those lower mass planets here, Earth and Venus would be here, we're really still not sensitive enough to discover these planets in large numbers. So we know very little about these objects. One of the main questions I think currently is whether the architecture of the solar system, outer giants, and the set of inner rocky planets that are relatively spaced out, is that a typical composition? And are planets that are Earth analogues, size of the Earth, mass of the Earth, and orbital distance around the G-type star, are these a common outcome of planet formation? And then another aspect, the third aspect I'd like to highlight here, is this transition region here. Now, it doesn't come out in this plot as well as it could, but there is actually a little bit of a gap here that separates planets that somehow have succeeded in accreting and retaining a relevant volatile envelope against planets that are essentially rocky with at best a small atmosphere on top of them. So these sub-Neptunes, these are very common, but they're yet to be really understood. We don't yet understand how they are made. Are they rocky core with a hydrogen envelope? Are they more Neptune-like? Do they have mixed volatile rich atmospheres? And what are their formation pathways? We don't have an analog in the solar system, so we'd like to use this exoplanet population to start understanding how they have formed and what fundamental properties of planet formation really produce them in such abundance. All right, so in my talk, I will mainly discuss results from 3 observatories that are out there to try and answer some of these questions. The first one, Angelica knows it very well. It's located down there on the Earth in Chile, a 1.2 meter telescope, Euler. Yeah. The second one is a little bit farther from the Earth. It orbits at an altitude of 700 meters. In low Earth orbit. It has an aperture of only 30 centimeters. That's CHEOPS. So this is really my daily bread in my work. And I will introduce CHEOPS in a lot more detail in the coming slides. And for the third telescope, we have to move about 1 year into the future. Launch is currently foreseen in the early first quarter of 2027. And we have to move to the second Lagrange point, about 1.5 million kilometers behind the Earth. And that, of course, is the PLATO satellite. That is an array of 26 cameras with 12 centimeter aperture. And PLATO is really going to be the next main transit survey. So the next satellite that is going to detect many thousands of new exoplanets. But let's go to CHEOPS for a second. What is CHEOPS? You can see a little rendition of CHEOPS there. It's an S-class mission, and S means small, which is the sort of the smallest category of ESA missions. And so it's relatively simple. It has one instrument that does exactly one thing. It's a photometer that does ultra-high precision photometry. We point one star at a time, and we have one very broad optical passband. So CHEOPS is also a partnership between 11 European countries and ESA. You can see the countries indicated here. And so Spain is also part of that. And some people here have also used CHEOPS in the past. So going relatively quickly through the timeline of CHEOPS, CHEOPS was adopted in 2014, was built and then tested thoroughly. Finally, it was launched on the 18th of December 2019 at 6 a.m. in the morning. And then there was commissioning, and the scientific mission started in March 2020. We quickly had the first scientific result, which is an occultation of an exoplanet. And then in 2023, CHEOPS concluded its nominal mission and started its first extension, building on a lot of exciting science and data that we had collected. And the really great news that we had 12 days ago was that actually CHEOPS has been extended a second time, and we will run through 27, 28, and 29. And it's not on my slide, but given I'm in Spain at the moment, I should mention that actually our Mission Operations Center is in Torrejón near Madrid. So thanks to you guys, we actually get to talk to the satellite and send our commands up there and bring back all of the exciting, beautiful science data. So let me first talk about this long period planets and some CHEOPS results that we've had going going in this direction, trying to detect these missing population of planets. One of the first really exciting results that we've had with CHEOPS was when CHEOPS observed this new Tulupi star. It was known to have 2 transiting planets. The test satellite had seen those transits, and a third radial velocity planet with a period of over 100 days. And so this is work by Leticia Del Rez, who at the time was a postdoc with us. But the goal of the observations were actually just to characterize better the radii of the inner 2 planets. They're both in this transition region between rocky and gas-rich atmospheres. So we went with CHEOPS and we observed first transits of the inner planet. They look pretty as you'd expect transit light curves to look. The depth of the transit, I should mention, it's only about 200 parts per million. That's quite small. Then we went to planet C, the second planet, got a transit that looked perfectly normal, and then a transit that had the little transit of planet B happening just before. So here we're just observing transits of the 2 planets, one after the other. But then the third observation of planet C looked like that, which is weird. Let's zoom in. We saw a flux decrease, another flux decrease, a rise in flux, and then the data continued sort of straight until the end of the observation. So what happened? Leticia really scratched her head a lot. And actually, it's quite logical. What we're seeing here is the third planet, the 107-day period planet, that is actually also aligned just in such a way that it does transit the star. And we were just totally not counting on that to happen because the probability for that is extremely small. And so what CHEOPS discovered here was a 3-planet system of small planets around a naked eye star with periods ranging from those very close in at a level of a few days out to over 100 days. And of course, we went back later and confirmed the transit of planet B there. If you look at the duration of the transit, it's actually quite long. This here is in days. Okay, we can go forward and study the composition of these planets a little bit. Just to summarize, what we could say is that the inner planet has relatively little volatiles, little water, whereas the outer planet, they must have significant fraction of water and a larger envelope of light gases, hydrogen or helium above that, or mixed into that. Yeah. Okay, but one system is great. What we really would like to have is many more systems. And the systems we'd like to discover are systems around bright stars, because bright stars will allow us to take radial velocity measurements, measure the masses, and then even study the atmospheres of these planets. So this plot here shows the population of planets on a radius against period diagram. And the yellow ones are the ones that are around bright stars. And so here really the test satellite comes in. It's very nice because it maps the sky in sets of about 1 month. And it detects single or double events, transits, sometimes years apart. And they are really promising to follow up, to measure the correct period, and then, of course, discover those far-out planets. And we have programs on ground-based facilities and with CHEOPS for the smaller planets to identify these. So I'd just like to highlight a couple of results from these programs. The first one that we studied with CHEOPS, this is work by Hugh Osborne, and this was the planet HIB 9618, where there were 2 small planets discovered by tests. One planet had a known period here, There was only one periodicity possible. But the other planet had only 2 transits and they were 2 years apart. So we know that between these 2 transits, n times the period of the planet must have passed. So we have discrete aliases that we can go forward and test. These are the aliases with their respective probability. And so we went and we tried the first one, flat, second one, flat, third one, flat. And you can kind of guess what's coming right now, right? On the 4th observation, we actually went and we identified the transit. And with that, we could identify the period to be 52 days. We are here having a system with 2 relatively longish period planets, 20 and 52 days, that are small. Okay, there's many more. We had this press release in 2023 of several small systems, and this really has become a bit of a pipeline. There's currently a large paper in preparation that will announce several more of such long period planets. But I'd also like to highlight here work that Angelica did during her PhD on a system with 2 transiting planets, where the outer one was again a transit that didn't have a precise period. But so what she actually did is she used radial velocity data from Espresso to identify the period of this 2.6 Earth radius planet to be about 35 days. Voila, so this is another and complementary way of getting the correct periods for these single transit alerts. As time goes on, of course, we're moving to longer and longer periods. Here's a result from Solène Ulma-Moll, who was a postdoc with us, and she's now an Ort Fellow in Leiden. And actually, as I said, we're moving to longer and longer periods, and this here was the first one that we've had at a period of over 100 days. Yeah, and here you can see a little bit of a summary of the new detections that are coming up, and you can see that we are really more and more efficiently filling out these longer period planets as we go along. And now this brings me to PLATO, right? I mentioned PLATO is really going to observe these long period planets, trying to find Earth analogues. So just to recap, PLATO is this array of smaller telescopes that point a large region of the sky in sort of a flower shape pattern. So the innermost region, this is where the 24 nominal cameras are going to overlap, and then outer regions are going to be covered only by fewer cameras. So their fields of view overlap in a strategic way to reach the optimal precision here in the center. And it will stare at this field for at least 2 years, maybe more. If you ask me, more is good. That will be decided a bit later on, and it's really also there to map out this region further out. But what I want to highlight is that, Earth here will also only get 2 transits if we observe for 2 years. So will we actually be able to detect Earth with PLATO? Oh yeah, not foreseen, I mentioned this, next year. And it's not so straightforward, because how we like to think of stars is what we see here. And then what stars are often really like is more like here on the right, with an Earth analog being extremely small, especially compared to the size of star spots. And here we're lucky because the sun is a relatively quiet star. Spots introduce long-term photometric variations, and then granulation, it adds the stochastic signal at short timescales that just adds this little noise level to our observation. Okay, so a study that we did with our PhD student Andreas was to actually take solar data and simulate solar data, add the transit of an Earth, and simulate PLATO observations of the sun based on this solar data. So here, this is actually solar data. This is from HMI. And what we did is that we actually added a little black dot that moves across the disk. And this way we simulate, and then we integrated over the whole thing, and we simulated an Earth transit this way. Yeah, here's a little video, and you can see the Earth going across like that. Yeah. So, okay, Andreas picked a timeline, some observations here, tested different impact parameters, so locations of the Earth on the solar disk. Yeah, tested on Earth. And we also tried this for different magnitudes, simulating different distances that a putative observer would be from the sun. And we also assumed that we had a very good knowledge on limb darkening of the subject. And this is the light curve that we got of a transit. So we can clearly see that there is some stochastic noise there, likely created by the granulation on the sun. And then if we look at the long term, we can see, of course, also some long-term trends around the Earth transit. So we simulated light curves with a single transit and then repeated the same thing at a separation of 360 days, adding a second Earth transit there, and then did a transit search on this light curve. And here's what we found. Down here you find the stellar magnitude. Here the impact parameter. So central transit and the very almost grazing transit. And what's green means that we found both transits correctly. Yellow means that we only found one, but the other one was incorrectly identified or not identified at all. And red means that we found nothing, or something that completely didn't correspond to what we put in. And so what this tells us, this study, is that up to magnitude 11.5, we're doing very good at finding both transits correctly and identifying the Earth apart from the very small impact, very high impact parameters. But then going to 12.5, we are starting to see really a lot of false positives. Yeah, why did I put the, yeah, okay. All right, and then we went on and we measured the parameters, doing different detrending approaches here. And we can actually nicely confirm then that down to magnitude 9.5, we get a measurement on the planetary radius with a precision of 3%, which is the mission goal of PLATO. So that's very reassuring for us. All right, so I mentioned also that we can characterize atmospheres of exoplanets. Here's just another illustration of transmission spectra. The light shines through the planetary atmosphere, and we see an imprint of lines in the stellar spectrum. This has, of course, been done amazingly well with JWST. This talk is not about JWST itself, but just to show you those very beautiful transmission spectra of a hot Jupiter, where we can see really an amazing diversity of absorption features, such as carbon dioxide. We see some water features here. We can even see some sulfur dioxide here that's created by photochemical reactions in the atmosphere. But then again, stellar activity makes life a little bit more difficult because it actually also affects transmission spectra and their interpretation. Now this is the I think by now very infamous transit light source effect. The point is that the light source of the star is not homogeneous, and the light that the planet covers during transit is not necessarily doesn't necessarily have the exact same spectral footprint as the disk integrated light, because there might be active regions. And at the same time, the planet can also pass in front of a stellar spot during transit, and that will create a bump if the spot is dark, or if we have a facular region, that can create sort of a dip in the curve of the transit. And while this is probably not so relevant for hot Jupiters, for the really small planets, this can be an issue. So this is a result from JWST by Moran et al., where they observed a super Earth, and these are the data they obtained. So there is some kind of a kink there, but it can be explained with two different models. The blue model is a water-rich atmosphere, but the orange model is simply a spotted star. So from those data alone, we cannot really say if there is water in the planetary atmosphere or if the star is just a little bit spotty. And so what my PhD student Ritam Chakraborty did was that he went on to simulate this type of phenomenon. So he used a pixelation approach to simulate the emergent spectrum of a star, and then placed a number of active regions on the star and allocated different spectra to these regions. Now, this approach it's not new. I mean, this has been done previously by other teams, but it's very nice to have our own little tool that does that. We then rotate the star, and we let the planet transit across it, and then basically we observe what happens to the transmission spectrum. Okay, yeah, it's called the SAGE. And at the same time, of course, we can determine the rotational flux integrated method. The rotational flux variations. Yeah, so the goal is to infer the spot or facular coverage from photometric variability, and at the same time predict how the contamination to the transmission spectra is going to evolve. And then fit planetary and stellar components together when interpreting transmission spectra. And we actually came to use this tool pretty quickly in the paper that was led by Dominique Petit, that dealt with some VLT observations of WESP 69, a beautiful, well-known hot Jupiter. And the transmission spectra looked a bit like this. So kind of flat, and then a sort of a drop to shorter wavelengths, which is a little bit odd. Typically, transmission spectra, they will have a rise to shorter wavelengths. Yeah, so we were a little bit confused, but we were like, okay, let's assume this is all good, and let's say it must be an active region. In this case, it must be a hotter active region that is on the star, or a large facular component that leads to this drop. And then at the same time, we noticed something really curious in simultaneous observations from two different sites. At the VLT, we observed an extra dip during transit. And honestly, I wouldn't have made much out of this extra dip, because there can be correlated noise in the data, you know, this happens. But at the same time, we observed a similar dip in the Euler-Cam observations that was taken at a different site. So this led us to believe that indeed at this point in time, the planet passed over a well-confined bright spot on the stellar surface, which then led us to conclude, well, there is indeed some strong hotter component on the stellar photosphere of this target. All right, we all know M stars are very active. So here's another very interesting set of observations that were also done by Ritam. And so Ritam studied this star that is very tiny, TOI 3884, an M4 star with a about half a Jupiter-sized planet orbiting it. This is a plot from a paper by Jose Almenara, where I believe he discovered the planet, or if not, it was one of the first follow-up papers. And what we can really see is that the light curves have this humongous asymmetry, and it's wavelength dependent. So in the infrared, in red here, the extra data show a smaller signal than the G-band LCOGT data. So clearly here, the planet is transiting over a huge spot on that star. And so this is really an idea that came from Jose and Ritam, was to just go and follow this planet up more through a multi-season campaign with EulerCam. And so here are the transits that went from 2023 down to 2025. And what we can actually see is that the feature is persistent. It stays there, but then at the same time, it does change a little bit in its exact shape from visit to visit. And so what Ritam then did is that he modeled these light curves, assuming one large polar or almost polar spot. And what he actually found is that the data are best explained if there is a spot that is just slightly offset from the stellar pole, and therefore, depending on when in the stellar rotation we're exactly seeing the observation, we're going to see the spot at a slightly different region, and that can reproduce this variations that we're seeing. It's a huge spot, almost 50 degrees in size. This little offset that I mentioned, it's about 5.5 degrees from the stellar pole. And it is stable over at least 3 years. And of course, from these observations, we can also measure precisely the inclination of the stellar spin axis and the spin orbit angles of star and planet. I should say, it's not on my slides, but of course, we made a prediction of the photometric variability that we'd expect from this model. And just when we were in the process of publishing the paper, that photometric variability was observed and published by a Japanese team. So we were extremely happy to see sort of our slightly wild model being confirmed. That made us very happy. All right, so the last thing, I will take a sip of water and then I will talk to you about the last thing that I'd like to highlight, coming back a little bit to CHEOPS. And that is about the formation and evolution of planets. And to study formation and evolution, well, what we really want to do is we want to study young planets, right? This is a very simplified figure that I made with the extreme, sophistication of Keynote. But in principle, the idea is that a planet, as it forms, it is still very much extended. It will cool down. The atmosphere will differentiate. There will be interaction with the planetary interior. The planet will cool, of course. It will contract. And so here are some much more sophisticated computations by the Zurich team. That actually show you how planets, depending on different starting conditions, how they contract over time. And then finally, of course, planets also have escaping atmosphere. So depending on their irradiation level and depending on their temperature, they might also be losing some of their atmosphere out to space. And one of the most exciting young system is the HIP 67522 system. It's a relatively young star. It's only 17 mega years old. Here's an artist's impression of that system. It hosts two planets, a 6 and a 14-day planet, and they both have gas giant sizes, right? 0.9 and 0.7 Jupiter radii. Yeah. What we know from JWST observations is that the inner planet is extremely puffy. As I said, the size of 0.9 Jupiter radii, but the mass is less than 20 Earth masses. So we have a small planet that is somehow bloated to look to the size of a giant. And what we also know is that actually the star has a preference of flaring in the direction of the planet. This was done from flare statistics of photometric observations of the system. All right, so we got very interested in the system, and Ritam got a large allocation of CHEOPS time to actually follow it up. But what you're seeing here is the test observations. And so you're seeing the long-term variability here, and you can see that it does change in size quite a bit from season to season. The data are gray, and blue is the model that Rita made to these data, allowing for active regions to be located at different stellar latitudes, and therefore through differential rotation merging and breaking apart a little bit. That creates this this change in the in the spot in the spot created variability. Yeah. The transits are indicated with the pink arrows. So they're really difficult to spot. But we can zoom in, and you can see the transits in the test data here. There's a stellar flare. And you can see that they're really superimposed on this massive planetary variability. And that they also do not seem to be fully flat. Like there seem to be some spot occultations that are occurring during the transits. And so we went and observed this object with CHEOPS 4 times. And you can see the uncorrected transits down here on the left. And then the transits with stellar activity, out of transit stellar activity corrected for to the best of our ability, but leaving the little brightening times intact during the transit. And next to it, you can see the best fit spot distributions that we find for these transits. And use this to actually, constrain the spot sizes and the spot temperatures, which are sort of in the ballpark of what makes sense. But what's actually almost more exciting here is that we also looked for transit timing variations. And as you can see, it's really flat. We did a dynamical analysis, and we therefore also inferred a mass limit for the outer planet, so an upper limit on the mass. And it's again really low. It's only 20 Earth masses again. So what we're seeing here is that also the outer planet in the system is yet another one of these extremely low density planets that we don't see in adult stars. So we're really seeing a planetary system that is at the very beginning of this evolutionary stage. And this is just me having a little bit of fun imagining that atmosphere. But this is my last, I think this is my last slide, second last. There is something that I want to highlight that is important when we're studying these very young planets. And that is that the transit depth changes depending on how many spots are actually on the star while we're looking at it, and whether or not the planet goes over a star spot during transit. And here on the right side, this is the measured planetary radius. And you can see that these here are fitting uncertainties. And you can see that, the apparent radius that we measure varies hugely. Here we measure a bit more than 9, and here we measure a bit more than 12 Earth radii. So actually what this means is that there is, for young planets, or more generally for planets orbiting active stars, there is a huge systematic uncertainty in the planetary size. And this is important because it impacts how we interpret the composition of the planet. So we went on and asked Johan Egger to make some compositional models of the planet and calculate the amount of the load of the gas-rich envelope of the planet. And depending on what radius assume, these are the two distributions that we find. And so when we make these models of planetary evolution, or when we make mass radius diagrams, we really have to be careful about which radius of the planet we're actually choosing. And so this is perhaps the little word of warning from this study that I'd like to impart on you. So to conclude, CHEOPS and PLATO, well, CHEOPS is going strong into extended mission 2. Detection moves to longer and longer periods. CHEOPS is confirming these long periods all over the sky, around bright stars. Exo-Earths will be detectable with PLATO, and PLATO will find several more of these long period planets in its staring region. Stellar activity is a really important aspect. Transits are a great way to scan the stellar photosphere, but we have to be really careful about stellar activity and how it biases our interpretation of planetary properties and transmission spectra. And these young planets are really exciting. We have these giant envelopes, low density atmospheres, and I think we are well advised to do more of these projects on young planets. And then this really is my final last slide, and that is an advertisement. So do it yourself, right? You can ask for your own CHEOPS data. The running call, so the GEO, the general observation, in extended mission 2 will be done through a rolling call. That means there's a deadline every month, and then 3 months after the deadline, the observations will start. It's open to absolutely everyone, and if you are interested in that, feel free to come talk to me. But also, check out the website, the ESA website. There's a lot of information. There's video tutorials, and there's also the ESA project scientist that sort of runs the GEO called Bruno Merin, located in Madrid. Feel free also to contact Bruno and talk to Bruno about this if you're interested. And with that, I am at the end. Thank you very much, and I hope you have a couple of questions.
Yes. So just a couple. For this Hipparcos 67522, can you go back to the slides where the maybe the one with the transit, or actually the one that shows the transit, the one before this one, yes. And this one. So you can actually see that the transits are already very different from the plots there, right? So I was wondering, this is not completely hopeless because you can also get photometry and then see at what phase of, let's say, what is the filling factor of spots at the time of your transit. Maybe try and run some corrections from there. So it might be supportive observations from the ground or from other facilities might be able to help there.
Absolutely.
So I think the point is very valid that this has to be done for these highly variable options.
Part of the motivations why we did this was because there were JWST programs coming up and we wanted to give them as much information as we could. Yeah.
So along these lines also, we are trying to help JWST observations by collecting ground-based supporting data, because then you can, in a way, not correct, but at least inform JWST process. Yeah, so that was a comment. And I have a question about the you early on with long period planets. It seems that there's already enough of a population to run some sort of differential analysis between the long period Jupiters and the short period Jupiters. Has this been done? Is there any systematic difference, radius inflation? Is there any evidence that there are population differences?
There are starting to be, there are some people looking into this with different aspects. So when it comes to radius inflation, it's very well known that it depends on the irradiation. So you can plot the Jupiter's size against the incoming radiation, and you see a very clear drop. So those really inflated ones are the very, very hot ones. Then another interesting aspect is actually the orientation of the orbit. And we find that the closer in ones are typically the less aligned ones. Sort of makes sense, right? Because they probably move there through planet scattering or quasi interactions. So something that involved like a high eccentricity and moving the planet out of the plane.
Composition-wise, is there any systematically investigated?
Yes, but it's a bit more difficult because when you do these transmission spectra, they're very good for hot planets, but for the longer period, cooler planets, I think up to now there are some observations, but I am not super on top of whether they have produced really some JWST comparable, like high quality results. But I think this will be very interesting.
Can I ask a very good question?
Sure.
Regarding the video that you showed, relation of sunlight, the
Yeah.
collective regions and
Yeah.
the transit of white planets. Did you consider an evolution of or that information states to be constant?
It was not a simulation. These are solar data. So
But planets seem to orbit quite fast, and the
yes,
active regions were not evolving.
that's a time scale thing. So that the planet of Earth across the sun takes 12 hours, whereas a solar rotation is 30 days. And the evolution of the solar active region is just happening on a time scale that is too long to see it in 12 hours.
I was
If you
thinking that the Earth light it would take longer.
Yeah, no.
Okay.
What would be very interesting is to actually take not only the data set near, but to do the full data set. So what I showed you is that we had 2 slabs of data, and in between we had a big gap, and that was for computational reasons. What I would really love to do is to actually have the full solar light curve and be very careful to keep the variability related to the active regions, because then there's also, I think there might be a higher risk of misinterpreting or having false positives of transits due to the perhaps some active region evolution. But this was hard to do for this study because on top of the solar variation, there was also a systematic effect from the spacecraft that did these solar observations that put a huge amplitude sinusoidal-like variability on top of the data. And so we corrected for that. And it was difficult to really retain those long timescale of months solar variability signals there.
Yes, question.
Yeah.
Okay. About this topic, planets, you mentioned, so correctly, you said that it's indication that it starts flaring towards the direction of the planet.
Yes, yes.
So we'll about magnitude.
Oof, if I knew. No. I cannot tell you about the mechanism behind because I honestly don't know. I can tell you about the observations. So this was a big press release. Was it 1 year ago or was it 2 years ago? Time goes fast. Was it last year? That they basically counted the number of flares depending on the planetary, as a function of the planetary orbital phase. And they found that always towards the planet is sort of statistically more likely that flares happen. How exactly? I guess there's some magnetic connection between the planetary atmosphere and the star, and then, yeah, something happens and the flares are more likely to go off, but I'm not an expert.
First question, what is this work? Right? You saw in next slides the variation. Yes, that affected the general structure. So in this kind of cases, like what is the procedure? Like what's the best way to follow so that we can adopt the best possible?
My proposition is to get the most possible data of the object, get a good photometric monitoring of the star, not only transits. Get transits as well, so that you can add the information of the location of the star, of the spot on the star. Try to build a good model of the whole stellar surface. And if you add to that high resolution spectra and activity indicators, I think you will, you improve on that. I really think that, to get a really accurate radius for these very active planets, I think we need a lot of data. And
so for this one, for example, what kind of radius is there? Now it ranges from 9 to 8.
That's what we wrote in the paper. I mean, the message here in the paper is, depending on when you look, you get a different radius. So we quote sort of a mean value, and then we add the systematic uncertainty as an additional error bar.
And another question I have is about the work of Andreas.
Yeah.
Where you saw the work that he did of the detectability of the transits based on the spectrum and the magnet. And then you saw the precisions that we both based on the magnet. Like, how much was it affected by the race in nature? Because like you saw how the uncertainty changed based on the magnitude, but I guess it changes a lot based on the race of the planet.
So it really becomes important for impact factors, I think above 7, where the transit becomes a lot shorter. So you just have a lot less data in transit, and it becomes less boxy as well. So your transit search algorithms are less efficient.
In these simulations, you used the 24 cameras, or you also decided to change?
No.
It's
24 cameras.
Yeah. So it's going to be really at the center of the field that PLATO will do well for Earth analogs, let's say.
Yeah.
Because as we go to 18 or something, then it probably loses a lot of.
Yes, this was really the optimal case, right? Remove half of the cameras, scale up the noise, you're going to have a hard time detecting. And so what I'm kind of advocating now at the moment is that actually what we should do is that we should have a list of these high, almost significant alerts, but not quite, and then take CHEOPS and wherever possible observe at the same time with the next transit that PLATO will cover the target, and then just double our signal to noise and bring those borderline cases over the edge.
Given these magnitudes, star magnitudes, the relatively small field, let's say, so the number of targets where this can be done must be quite small, right? Are you talking about hundreds, or in the battlefield? Cannot be a lot, right? Where you can actually have the right magnitudes for your simulations and be in the 24 camera field, subfield.
Yeah, I don't know the exact number.
It would be good maybe to monitor this 100.
Yeah, absolutely.
Targets.
Honestly, I think whenever we can to reobserve and do anything about this handful of very good candidates from PLATO that we should do, I think we have to do it. These are really the most valuable planets to come, right? I mean, sure, we're interested about 20-day period, mini Neptunes or something, but they're really like the really special ones that will tell us about Earth and our place in the cosmos, the whole story. Those are the very long period.
Okay. Monika Lendl.
You're very welcome.
Yeah.
Alba.
How do I get out of this?
Yeah, it looks similar because we see no map.